Introduction to HKDF. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we are diving deep into HKDF, which stands for HMAC-based Key Derivation Function. This is one of the most important cryptographic primitives used in modern systems, and you will find it everywhere from TLS 1.3 to cloud encryption services. HKDF is defined in RFC 5869, and it is built on top of HMAC, which itself is built on top of hash functions like SHA-256 or SHA-512. So, why do we need key derivation functions in the first place? Well, in cryptography, we often start with a source of key material that might not be uniformly random, or it might not be the right length for our needs. For example, you might perform a Diffie-Hellman key exchange and get a shared secret. But that secret might have some statistical weaknesses, or it might not be exactly 256 bits for your AES key. HKDF solves this problem by taking that input key material and deriving cryptographically strong keys of any desired length. What makes HKDF special is its two-phase approach. It has an extract phase and an expand phase. The extract phase takes your possibly weak input key material and assault, then produces a pseudorandom key. The expand phase then takes that pseudorandom key and expands it into as many output key bytes as you need. This separation is elegant because you can extract once and then expand multiple times to derive different keys for different purposes. In cloud environments, HKDF is used extensively. AWS uses it in their encryption SDKs. Azure uses it in key vault operations, and it is fundamental to TLS connections that secure all your API calls. Understanding the mathematics behind HKDF will help you make better security decisions and debug cryptographic issues when they arise. HMAC Foundation. Before we can understand HKDF, we need to understand HMAC, because HKDF is literally HMAC-based. HMAC stands for Hash-Based Message Authentication Code, and it is a way to create authenticated checksums using a hash function and a secret key. The beauty of HMAC is that it takes any cryptographic hash function like SHA-256 and turns it into a keyed hash function. The HMAC construction was designed to prevent linked extension attacks that plagued simpler constructions like just concatenating a key with a message and hashing them together. The HMAC formula involves two hash operations with two different padded versions of the key. We use two padding constants: IPAD, which is the byte 0x36 repeated, and OPAD, which is the byte 0x5c repeated. These values were chosen to have good mathematical properties and differ in several bit positions. The outer hash operation takes the key XOR'd with OPAD, concatenates it with the inner hash result, and hashes that. The inner hash operation takes the key XOR'd with IPAD, concatenates it with the message, and hashes that. This double hashing structure is what makes HMAC secure against various cryptographic attacks. Why does this matter for HKDF? Because HKDF uses HMAC as its underlying primitive in both the extract and expand phases. Every operation in HKDF is essentially an HMAC call with carefully chosen inputs. When we extract, we are calling HMAC with the salt as the key and the input key material as the message. When we expand, we are calling HMAC multiple times with the pseudorandom key as the HMAC key. The security of HKDF relies entirely on the security of HMAC, which itself depends on the security of the underlying hash function. If you are using HKDF SHA-256, you are depending on SHA-256's collision resistance and preimage resistance. This is why choosing a strong hash function is critical. In production systems today, SHA-256 is the minimum recommended strength, with SHA-384 or SHA-512 being used for higher security requirements. HKDF extract phase mathematics. Now let's get into the actual mathematics of HKDF, starting with the extract phase. The extract phase is deceptively simple, but understanding what it accomplishes is crucial. The goal of extract is to take your input key material, which might be unevenly distributed or not fully random, and compress it into a pseudorandom key of fixed length. The extract function takes three inputs: a salt, your input key material, abbreviated as IKM, and the choice of hash function. The salt should be a random value, but if you do not have one, you can use a string of 0 bytes equal to the hash length. The salt acts as a key to the HMAC function in this phase. Mathematically, PRK equals HMAC using the hash function, with salt as the key, applied to the input key material. Why use the salt as the HMAC key rather than the IKM? This is a subtle but important design decision. By using the salt as the key, we ensure that even if an attacker has some knowledge about the structure of your IKM, they cannot exploit that knowledge without also knowing the salt. The salt effectively acts as a randomizing element that breaks any patterns in the IKM. The output of the extract phase is the pseudorandom key, or PRK. This PRK is exactly the length of the hash function output. For SHA-256, that's 32 bytes. For SHA-512, that's 64 bytes. This PRK is now suitable for use as a cryptographic key in the expand phase. It has been processed through HMAC, which means it has the statistical properties we need for key derivation. In practice, you might wonder when you actually need the extract phase. If your input key material is already a uniformly random string of the right length, like a key you generated from a proper CSPRNG, you might skip extract and use that key directly as the PRK in the expand phase. However, for most real-world scenarios like Diffie-Hellman key exchanges or password-based key derivation, the extract phase is essential. It involves taking your shared secret or password-derived value and turning it into something cryptographically suitable for key derivation. HKDF expand phase mathematics. The expand phase is where HKDF really shows its power. Once you have your pseudorandom key from the extract phase, you can expand it into as many bytes of key material as you need. You might need 32 bytes for an AES-256 key, or you might need 96 bytes because you are deriving an encryption key, AMAC key, and an IV. The expand phase handles all of this elegantly. The expand function takes 4 inputs: the pseudorandom key PRK from extract, some optional context information usually called info, the desired length of output key material L, and the hash function. The info parameter is really important because it allows you to derive different keys for different purposes from the same PRK. For example, your info might be the string encryption key for one derivation and MAC key for another derivation. The mathematical process of expand is iterative. We generate output blocks T1, T2, T3, and so on until we have enough bytes. The first block T1 is computed as HMAC, using PRK as the key, applied to the concatenation of the info string and the byte 0x01. The second block T2 is HMAC, using PRK as the key, applied to the concatenation of T1 info and the byte 0x02. Each subsequent block includes the previous block in its input. This chaining of previous outputs into the next HMAC call is crucial for security. It means that each output block depends on all the previous blocks, which prevents certain types of attacks. The counter byte at the end, starting at 0x1 and incrementing, ensures that each block is unique even if the info parameter is the same. The maximum value of this counter is 255, which means you can derive at most 255 times the hash length in output bytes. For SHA-256, that's 255 times 32, which equals 8160 bytes of key material. Once you have generated enough T blocks, you concatenate them together and truncate to exactly L bytes. So, if you asked for 50 bytes with SHA-256, you would generate T1, which is 32 bytes, and T2, which is another 32 bytes, giving you 64 bytes total. Then, you would take the first 50 bytes of that concatenation. The info parameter deserves special attention in cloud deployments. This is where you encode application-specific context. You might include the protocol name, version number, user identifier, or purpose of the key. This binds your derived keys to specific contexts and prevents key reuse across different scenarios. Complete HKDF process flow. Let's put the entire HKDF process together now that we understand both phases. When you call HKDF, you are executing a two-phase process that transforms input key material into one or more derived keys. This process is deterministic, meaning the same inputs always produce the same outputs, which is important for both parties in a key agreement protocol to derive the same keys independently. The complete process starts with your input key material, which might be a Diffie-Hellman shared secret, an ECDH shared points X coordinate, or any other source of cryptographic material. You also need to choose your salt. The salt should ideally be a random value of the same length as your hash function output, but it can be shorter or even empty if necessary. The salt does not need to be secret, but it should be different for key derivation operations whenever possible. In the extract phase, you call HMAC with the salt as the HMAC key and the IKM as the message. This produces your pseudorandom key, PRK. This PRK is now statistically uniform and suitable for cryptographic use. It's the intermediate value that bridges the two phases. You can think of extract as a randomness extractor, taking potentially weak input and producing strong output. In the expand phase, you call HMAC iteratively, using the PRK as the HMAC key. You achieve this by chaining together blocks with your information context and incrementing counters. You continue this process until you have generated enough output bytes for your needs. Each HMAC call produces one hash length worth of output, and you concatenate these blocks together. The final step is truncating the output to your exact requested length, L. What is elegant about this design is its flexibility. You can extract once with expensive input material, like a Diffie-Hellman operation, then expand multiple times cheaply to derive many different keys. Each expansion can use different info parameters to domain separate the keys. The security proof of HKDF shows that as long as HMAC is a pseudorandom function, the outputs of HKDF are computationally indistinguishable from random strings. This means your derived keys are just as good as if you had generated them randomly, which is exactly what we want from a key derivation function. Example with SHA-256. Let's walk through a concrete example of HKDF using SHA-256 to make all this mathematics tangible. We'll derive a 42-byte output key from some input key material, which is a common scenario you might encounter when deriving an AES-256 key plus an initialization vector. This example will show you exactly what bytes go where and how the chaining works. First, let's set up our inputs. Our input key material IKM will be a 32-byte value. Let's say it is from an ECDH shared secret. Our salt will be a 16-byte random value. These are realistic sizes you would see in production. The info parameter will be the string application key version 1, which provides context about what this key is for. We want 42 bytes of output, which is more than one SHA-256 hash length, so we will need to generate two blocks. In the extract phase, we call HMAC-SHA-256 with the 16-byte salt as the HMAC key and the 32-byte IKM as the message. Remember that HMAC internally pads keys to the block size, which for SHA-256 is 64 bytes. So the salt gets padded with zeros to 64 bytes before being XOR'd with IPAD and OPAD. The output of this HMAC call is RPRK, which is exactly 32 bytes because SHA-256 always outputs 32 bytes regardless of input size. Now for the expand phase. We need to generate enough blocks to get 42 bytes. Since each SHA-256 block is 32 bytes, we need 2 blocks. For T1, we call HMAC-SHA-256 with PRK as the key, and the message is the concatenation of the empty string T0, our info string application key V1, and the byte 0x01. This produces 32 bytes. For T2, we call HMAC-SHA-256 with PRK as the key, and the message is T1 concatenated with info and the byte 0x02. This produces another 32 bytes. We now have 64 bytes total from T1 and T2 concatenated together. We truncate this to the first 42 bytes to get our final output key material. Those 42 bytes are now cryptographically suitable for use as key material. You might use the first 32 bytes as an AES-256 key and the remaining 10 bytes as part of an IV or nonce. The important thing is that these bytes are computationally indistinguishable from random, assuming HMAC-SHA-256 is secure. Security properties and proofs. The security of HKDF rests on several mathematical properties that have been formally proven. Understanding these properties helps you use HKDF correctly and understand its limitations. The primary security property we care about is that HKDF outputs are pseudorandom. This means no efficient algorithm can distinguish HKDF outputs from truly random strings without knowing the secret input key material. The formal security proof of HKDF was provided in the original paper by Hugo Kravchuk. The proof shows that if HMAC is a pseudorandom function, then HKDF extract produces a pseudorandom key from the input key material, and HKDF expand produces pseudorandom output from that key. This is proven using a sequence of games where we replace real components with ideal random functions and show that an adversary cannot tell the difference. One crucial security property is collision resistance in the expand phase. Because we chain previous blocks into the next HMAC computation, an attacker cannot cause two different info contexts to produce the same derived key. The counter byte ensures that even with the same PRK and info, different positions in the output stream produce different values. This prevents key reuse attacks where the same key might be used in different contexts. The extract phase provides what is called randomness extraction. Even if your input key material has some structure or predictability, as long as it has enough min entropy, the extract phase will produce a uniformly random PRK. The formal bound shows that an adversary needs roughly 2 to the power of hash length divided by 2 queries to distinguish the PRK from random. For SHA-256, that is 2 to the 128, which is computationally infeasible. However, HKDF is not a miracle. It cannot create randomness from nothing. If your IKM has very low entropy, like a weak password, HKDF alone won't save you. This is why password-based key derivation uses different functions like PBKDF2 or Argon2 that include iteration counts to slow down brute force attacks. HKDF assumes you start with reasonably good key material. Also, HKDF security depends entirely on keeping the PRK secret. If an attacker learns your PRK, they can derive all the same keys you can. Parameter selection guidelines. Choosing the right parameters for HKDF is critical for security and interoperability. Let's talk about how to select your hash function, salt, info parameter, and output length based on your specific requirements. These choices affect both security and performance, so understanding the trade-offs is important. For the hash function, SHA-256 is the minimum recommended strength today. SHA-1 should never be used for new designs because of its collision vulnerabilities. SHA-256 provides 128 bits of security against collision attacks and 256 bits against preimage attacks. If you need higher security, SHA-384 or SHA-512 are good choices. SHA-512 is particularly efficient on 64-bit platforms. The hash function you choose determines your maximum output length, with SHA-256 allowing up to 8160 bytes and SHA-512 allowing up to 16320 bytes per HKDF call. The salt should ideally be a random value of the same length as your hash output. For SHA-256, that's 32 bytes of random data. The salt does not need to be secret, but it should be unique for each distinct key derivation when possible. In protocols, the salt often includes session identifiers or nonces. If you absolutely cannot provide a salt, using all zeros is acceptable, but you lose the randomization benefits. Never reuse the same salt with the same IKM for different purposes, as this would produce the same PRK. The info parameter is your domain separation mechanism. This should encode everything that distinguishes one key derivation from another. Common practices include concatenating a protocol name, version number, key purpose identifier, and any contextual information like user IDs or session IDs. For example, TLS 1.3, client handshake traffic secret, is a valid info string. The info parameter can be empty if you're only deriving one key and don't need domain separation, but using info is considered best practice. For output length L, you should request exactly the number of bytes you need, no more. If you need a 256-bit AES key, request 32 bytes. If you need both an encryption key and AMAC key, you have two choices. Either derive them in one call with concatenated info parameters, or make separate HKDF calls with different info values. The second approach is cleaner and provides better domain separation. Be aware of the maximum output length limitation, which is 255 times the hash length. For most applications, this is more than sufficient. Implementation considerations. Implementing HKDF correctly requires attention to several important details. While the algorithm is straightforward, getting the byte-level details right is crucial for security and interoperability. Let's walk through the key implementation considerations you need to be aware of whether you're using a library or implementing HKDF yourself. First and foremost, use a well-tested cryptographic library rather than implementing HKDF from scratch. Libraries like OpenSSL, BoringSSL, Libsodium, and cryptography libraries in Python, Go, and Rust all provide HKDF implementations that have been audited and tested. These libraries handle the byte manipulation correctly and avoid common pitfalls like timing attacks or incorrect padding. In Python, you can use the cryptography library. In Go, you would use the golang.org/x/crypto/HKDF package. In Node.js, the crypto module has built-in HKDF support. When you do use a library, pay attention to the API. Some libraries provide separate extract and expand functions, letting you call them independently. Others provide a combined HKDF function that does both phases. Some libraries let you pass none or null for the salt to use all zeros automatically. Understanding your library's API prevents mistakes like passing parameters in the wrong order or using the wrong encoding for strings. Byte encoding is a common source of bugs. When you have a string, such as the info parameter application key version 1, that needs to be converted to bytes. Always use UTF-8 encoding consistently. Never use platform-dependent encodings. The salt and IKM are typically already bytes from random number generators or cryptographic operations, but if you are deriving them from passwords or other strings, encode them properly. Length prefixing can help prevent ambiguities where different combinations of parameters could produce the same byte string. Memory management matters for security. The PRK and output key material are sensitive values that should be cleared from memory once they are no longer needed. In languages with manual memory management, zero out key buffers explicitly. In garbage-collected languages, this is harder, but some libraries provide secure buffer types. Never log or print key material during debugging. Never store keys in plain text on disk unless they are in a proper key management system. These operational security measures are just as important as getting the algorithm implementation right. Testing your HKDF implementation is essential. RFC 5869 includes test vectors you should verify against. Test with different hash functions, different input sizes, and edge cases like empty salts or info parameters. Test the maximum output length to ensure you handle the counter byte correctly. Test that extract and expand can be called separately and produce the same results as a combined call. Interoperability testing with other implementations is valuable to catch encoding or byte order issues. Common use cases and patterns. HKDF appears in numerous real-world protocols and systems. Understanding these common use cases helps you recognize when HKDF is the right tool and how to apply it effectively. Let's explore several patterns where HKDF excels and see how major protocols use it in practice. The most common use case is TLS 1.3 key derivation. TLS 1.3 extensively uses HKDF for deriving all traffic keys from the handshake shared secrets. After an ECDHE key exchange, both client and server derive the same handshake secret using HKDF extract with the ECDHE shared secret as IKM and a transcript hash as salt. Then they use HKDF expand multiple times with different info labels, like client handshake traffic secret and server handshake traffic secret, to derive separate keys for each direction. This provides perfect forward secrecy and clean key separation. Another major use case is in encrypted messaging protocols like Signal. Signal uses the X3DH key agreement protocol, which results in multiple Diffie-Hellman outputs. These outputs are concatenated and fed into HKDF extract to produce a single root key. Then HKDF expand derives separate chain keys and message keys. Each message uses a unique key derived through this chain, providing strong security properties. The info parameter encodes the message sequence number and direction. Cloud key management services use HKDF extensively. When you use a WSKMS envelope encryption, the data key provided to you was derived using HKDF-like operations from the master key. Azure Key Vault uses HKDF when deriving keys for different services from root keys. Google Cloud KMS similarly uses key derivation trees where HKDF expands root keys into service-specific keys. The hierarchical nature of HKDF makes it perfect for these key tree structures where you have a root secret and need to derive many child keys. In VPN and tunnel protocols, HKDF derives encryption and authentication keys from the shared secret established during the handshake. WireGuard uses HKDF as part of its noise protocol framework for deriving all session keys. IPsec IKEv2 can use HKDF as its PRF for key derivation. The pattern is always the same. One shared secret goes in. Multiple purpose-specific keys come out through different expand operations with unique info values. Password managers and encrypted storage systems use HKDF after the initial password derivation. They will use PBKDF2 or Argon2 to derive a key from your master password, then use that key as IKM to HKDF to derive separate keys for encryption, authentication, and search indexing. This separation means a compromise in one area does not automatically compromise others. The info parameter might include the user ID, vault ID, or item type to ensure keys are specific to their purpose. HKDF versus other key derivation functions. Understanding how HKDF compares to other key derivation functions helps you choose the right tool for your specific use case. There are several other KDFs in common use, each designed for different scenarios. Let's compare HKDF with PBKDF2, scrypt, argon2, and simple hash-based derivation to see where each excels and where they fall short. PBKDF2 is probably the most well-known alternative. PBKDF2 stands for Password-Based Key Derivation Function 2, and as the name suggests, it is designed specifically for deriving keys from passwords. The key difference is that PBKDF2 includes an iteration count parameter that controls how many times the underlying PRF is called. This makes it intentionally slow, which defends against brute force attacks on weak passwords. A typical PBKDF2 configuration might use or even iterations. HKDF, by contrast, is designed to be fast because it assumes you are starting with high-entropy key material, not a user password. Scrypt and argon2 are memory hard key derivation functions designed for password hashing. They not only require many iterations like PBKDF2, but they also require large amounts of memory, making them resistant to specialized hardware attacks using ASICs or GPUs. Argon2 won the password hashing competition in 2015 and is considered the state-of-the-art for password-based key derivation. These functions are overkill if you are starting with a good cryptographic secret like a Diffie-Hellman shared value. They are also much slower than HKDF, which matters in high-performance applications. Some older protocols use simple hash-based key derivation, just hashing the input key material concatenated with a counter or label. This approach lacks the formal security analysis that HKDF provides. Without the extract phase, you don't get the randomness extraction property. Without the expand phases chaining structure, you lose some security guarantees. These simple schemes are acceptable in some cases, but HKDF is preferred because of its proven security properties and standardization in RFC 5869. So when should you use each? Use PBKDF2, scrypt, or argon2 when deriving keys from passwords or other low-entropy user inputs. Use HKDF when you have high-entropy key material from cryptographic operations like key exchanges, random number generators, or existing keys. If you need to derive a key from a password and then expand it, you might use argon2 first to get a strong key, then feed that into HKDF for expansion. This layered approach combines the strengths of both types of functions. HKDF in TLS 1.3 Deep Dive. TLS 1.3 makes extensive use of HKDF throughout its handshake and key derivation process. Understanding how TLS 1.3 uses HKDF provides a real-world example of best practices and shows you how to structure key derivation in your own protocols. TLS 1.3 was designed from the ground up with HKDF as a core primitive, replacing the more ad hoc PRF constructions used in earlier TLS versions. The TLS 1.3 key schedule starts with an early secret derived from a pre-shared key if one exists, or from all zeros if not. This early secret is then used as input to derive the handshake secret after the Diffie-Hellman key exchange. The pattern is to use HKDF extract with the previous secret as the salt and the new input key material as the IKM. This creates a chain of secrets where each stage depends on all previous stages, providing strong security properties. After deriving the handshake secret, TLS 1.3 uses HKDF expand with different labels to derive the client and server handshake traffic secrets. The labels are strings like CHS traffic for client handshake traffic, and SHS traffic for server handshake traffic. These labels are concatenated with transcript hashes to bind the keys to the specific handshake messages. This is a perfect example of using the info parameter for domain separation and context binding. From each traffic secret, TLS 1.3 further derives specific keys for encryption and authentication. It calls HKDF expand with labels like key to derive the actual AES key, and IV to derive the initialization vector. This hierarchical key derivation means you have multiple layers, Early secret leads to handshake secret leads to traffic secrets lead to actual encryption keys. Each layer is derived using HKDF with appropriate labels and context. One particularly elegant feature of TLS 1.3's use of HKDF is key updates. During a long-lived connection, either party can request a key update by deriving new traffic secrets from the current ones using HKDF expand with the label traffic upd. This provides forward secrecy even after the initial handshake, because compromising the current keys does not reveal previous keys. The mathematical properties of HKDF ensure that you cannot work backwards from a derived key to the parent key. TLS 1.3 is the gold standard for how to use HKDF in a complex protocol with multiple security requirements. Advanced topics: multi-stage extraction. While HKDF is typically described as having one extract phase, followed by one or more expand phases, you can actually chain multiple extract operations together to create sophisticated key derivation hierarchies. This multi-stage extraction pattern is useful when you have multiple sources of key material that you want to combine, or when building key trees where intermediate keys need to be derived from multiple parent keys. The concept is simple but powerful. Instead of doing one extract operation, you do a sequence of extracts where the output of one extract becomes the salt for the next extract. For example, suppose you have three sources of key material: IKM1 from an ECDH exchange, IKM2 from a pre-shared key, and IKM3 from a session ticket. You could first extract with IKM1 to get PRK1, then extract again with PRK1 as the salt and IKM2 as the input to get PRK2, then extract once more with PRK2 as the salt and IKM3 as the input to get your final PRK. This chaining structure means that your final PRK depends cryptographically on all the input key materials. An attacker would need to compromise all three sources to derive the same final key. This is exactly what TLS 1.3 does with its key schedule, chaining together the pre-shared key, ECDH shared secret, and transcript hashes through multiple extract operations. Each extract operation adds more entropy and more dependencies into the final key. From a security perspective, multi-stage extraction maintains all the security properties of single-stage extraction, as long as each HMAC call is secure. The mathematical proof extends naturally because each stage is just another HMAC operation. The advantage is composability. You can build complex key derivation schemes by composing simple HKDF operations. This is much cleaner than trying to design a single monolithic key derivation function that handles all cases. When would you use multi-stage extraction in practice? Consider a scenario where you have both long-term and ephemeral key material. You might extract the long-term key first to get a root key, then extract again with the ephemeral material to get a session key. Or in a multi-party protocol, you might extract sequentially with key material from each party, building up a shared key that depends on everyone's contributions. The flexibility of HKDF makes these patterns straightforward to implement securely. Performance optimization strategies. While HKDF is already quite efficient compared to password-based KDFs, understanding its performance characteristics helps you optimize your implementation for high-throughput applications. Let's explore where the computational cost lies and how to minimize overhead when deriving keys at scale, such as in TLS termination proxies or high-volume API gateways. The computational cost of HKDF comes primarily from HMAC operations, and HMAC cost comes from the underlying hash function. For SHA-256, each HMAC requires 2 SHA-256 hash computations. The extract phase does 1 HMAC, so that's 2 SHA-256 hashes. Each block in the expand phase does 1 HMAC, so that's 2 more SHA-256 hashes per block. If you're deriving 64 bytes with SHA-256, you need 2 expand blocks, which means 6 SHA-256 operations total. 2 for extract and 4 for expand. Hardware acceleration is your friend. Modern CPUs have SHA extensions that dramatically speed up SHA-256 and SHA-512 computations. Intel's SHA-NI and ARM's crypto extensions can provide 10x or more speedup compared to software implementations. Make sure your cryptographic library is compiled to use these instructions. OpenSSL and Boring SSL automatically detect and use hardware acceleration when available. You can verify this is working by checking your CPU flags for SHA-NI on Intel or SHA-1 and SHA-2 on ARM. If you're doing multiple derivations from the same IKM, you can optimize by caching the PRK from the extract phase. Extract once, then expand multiple times with different info parameters. This is especially valuable in protocols like TLS 1.3, where you derive many keys from a single handshake secret. The PRK is secret and must be protected, but caching it in memory for the duration of a session can have your HMAC operations. Batch processing can also help in some scenarios. If you are deriving keys for many connections simultaneously, you might be able to benefit from SIMD parallelism in your hash implementation. Some libraries support processing multiple hash inputs in parallel using AVX2 or AVX512 instructions. This will not help for a single HKDF operation since the expand blocks must be computed sequentially due to chaining, but it can help if you are doing many independent HKDF operations. Finally, consider your hash function choice carefully. SHA-256 is the standard, but SHA-512 is actually faster on 64-bit platforms because it uses 64-bit words internally. On a modern x86-64 CPU, SHA-512 can be faster than SHA-256 per byte, and it produces larger output blocks, which means fewer expand iterations. If you need 96 bytes of key material, SHA-256 requires 3 blocks while SHA-512 requires only 2. The trade-off is that SHA-512 HMAC operations consume more memory bandwidth. Profile your specific workload to determine which hash function gives the best performance for your use case. Common pitfalls and how to avoid them. Even though HKDF is relatively simple, developers often make several common mistakes when implementing or using it. Let's go through the most frequent pitfalls and learn how to avoid them. These lessons come from security audits, bug reports, and real-world incidents where incorrect HKDF usage led to vulnerabilities. The first major pitfall is reusing the same salt and IKM combination for different purposes. Remember, HKDF is deterministic. If you call it with the same inputs, you get the same output. This might seem obvious, but it is easy to make mistakes. For example, if you derive encryption keys for 2 different sessions using the same master key as IKM and no salt or the same salt, you will get the same derived keys. This breaks security completely. Always ensure uniqueness either through unique salts, unique info parameters, or both. In session-based protocols, include a session ID in the info parameter. Another common mistake is using HKDF with password-derived input without proper password stretching first. Developers sometimes think that HKDF's extract phase will strengthen a weak password, but it won't. HKDF does one HMAC operation, which is far too fast to resist brute force attacks on passwords. If you need to derive a key from a password, always use a proper password-based KDF like Argon2 or PBKDF2 first, with a high iteration count, then use that output as IKM to HKDF. Never feed passwords directly into HKDF. Improper encoding of the info parameter causes subtle bugs. If you concatenate multiple values into your info parameter without delimiters, you can get ambiguities. For example, if your info is meant to be a user ID combined with a purpose string, The bytes of user 123 plus purpose are the same as user 12 plus 3 purpose. Use explicit linked prefixing or fixed separators like null bytes or pipes. Better yet, use a structured format like concatenating length of user ID bytes, length of purpose bytes. This prevents any ambiguity. Another common pitfall is incorrectly truncating the output. Some developers generate more bytes than needed and simply take the beginning, which is correct. However, others try to take bytes from the middle, or generate fewer bytes than needed, hoping to save computation. You should always generate at least as many bytes as you need and truncate from the beginning. The security proofs assume you are taking a prefix of the output, not arbitrary bytes from the middle. Finally, there is the mistake of not keeping the PRK secret. The PRK is just as sensitive as your final derived keys. If an attacker obtains your PRK, they can derive all the same keys you can. Store PRK in protected memory, clear it when done, and never log or transmit it. Some implementations make the mistake of storing PRK in a configuration file or database, thinking it is just an intermediate value. Treat PRK with the same care you would treat any cryptographic key. If you are implementing a protocol that requires PRK to be stored long-term, encrypted with a key from your key management system. HKDF in Cloud Key Management Systems. Cloud key management systems from AWS, Azure, and Google Cloud all leverage key derivation functions like HKDF internally for various purposes. Understanding how these platforms use HKDF helps you design better cloud-native applications and make informed decisions about key management. While the exact implementation details are proprietary, the general patterns are well understood and documented. AWS Key Management Service uses key derivation extensively in its envelope encryption model. When you call Generate Data Key, KMS uses your customer master key as input to a key derivation function to produce a unique data key. While AWS does not publicly specify using HKDF exactly, the concept is the same. Derive unique keys from a master key using contextual information. The encryption context you provide becomes part of the derivation input, similar to HKDF's info parameter. This binds the derived key to specific context like the S3 bucket name or user ID. Azure Key Vault similarly uses key derivation for operations like key wrapping and unwrapping. When you use a key in Key Vault to protect data, Azure derives working keys from your stored key using context information. The benefit is that your actual key never leaves the hardware security module. Only derived keys are used for encryption operations, and these derived keys are ephemeral. If you're using Azure Key Vault Managed HSM, you can even implement your own key derivation schemes on top of stored keys using the cryptographic operations API. Google Cloud KMS takes a similar approach with its key hierarchy. A root key in Cloud HSM can derive multiple key versions, and each key version can derive working keys for specific operations. The key version number and operation context flow into the derivation function, ensuring that each derived key is unique and bound to its purpose. GCP's Tink cryptographic library, which is open source, uses HKDF extensively and shows best practices for how Google thinks about key derivation. The pattern across all three cloud providers is consistent. Use a small number of highly protected master keys to derive many purpose-specific working keys. This reduces the attack surface because you only need to protect the master keys, and it provides operational flexibility because you can derive keys on demand rather than storing thousands of individual keys. When you design applications on these platforms, think about how you can leverage their key derivation capabilities to minimize the number of keys you need to manage directly while maximizing security through context binding. Testing and validation strategies. Testing cryptographic implementations is critical but also challenging. You need to verify not just that your code works, but that it produces exactly the right outputs for given inputs and handles edge cases securely. For HKDF, comprehensive testing involves unit tests with known test vectors, property-based testing, integration testing, and security testing. Let's explore each type of testing you should perform. RFC 5869 provides official test vectors that you must test against. These test vectors specify exact inputs for IKM, SALT, and info parameters, along with the expected PRK and OKM outputs. Your implementation must produce byte-for-byte identical results. Test vectors are provided for multiple hash functions including SHA-256 and SHA-1. Even though SHA-1 is deprecated, testing against its vectors helps verify your implementation logic is correct. Create unit tests that load these test vectors and assert that your HKDF functions produce the expected outputs. Property-based testing, also known as fuzzing in some contexts, involves testing general properties that should always hold rather than specific input-output pairs. For HKDF, properties you should test include determinism, meaning the same inputs always produce the same outputs. Output length, meaning you always get exactly L bytes when you request L bytes. And collision resistance, meaning different info parameters should produce different outputs with high probability. Use frameworks like Hypothesis in Python or QuickCheck in Haskell to generate thousands of random test cases and verify these properties hold. Integration testing verifies that HKDF works correctly in your larger system. If you're using HKDF as part of ATLS implementation, test the full handshake and verify that both parties derive identical keys. If you're using HKDF for database encryption, test that you can encrypt data, derive the same key later, and decrypt successfully. Integration tests should cover realistic scenarios including key rotation, concurrent access patterns, and error conditions like invalid key material. Security testing is the process of verifying that your implementation does not leak information through side channels. Timing attacks are a major concern in cryptography. Your HKDF implementation should take the same amount of time regardless of the input values to prevent timing analysis. Use constant time comparison functions when checking keys or PRKs. Test for memory leaks by monitoring your process memory after deriving keys and ensuring sensitive material is cleared. Run your code through static analysis tools like Coverity or CodeQL to catch buffer overflows, use after free bugs, or other memory safety issues. Finally, conduct code reviews with security-focused developers or engage external security auditors. Cryptographic code is subtle and even experienced developers make mistakes. A second pair of eyes often catches issues that automated testing misses. Document your test coverage and make it part of your CI/CD pipeline so that every code change is validated against all test suites before deployment. HKDF and quantum resistance. With the advent of quantum computers, cryptographic security is evolving. While practical large-scale quantum computers do not exist yet, the cryptographic community is preparing for their eventual arrival by developing post-quantum cryptographic algorithms. Understanding how HKDF fits into a post-quantum world is important for long-term security planning. The good news is that HKDF based on SHA-256 or SHA-512 is believed to be quantum resistant for its core functionality. Quantum computers break certain types of cryptographic algorithms, specifically factorization-based systems, like RSA, and discrete logarithm systems, like traditional Diffie-Hellman and ECC. However, symmetric cryptography and hash functions are much more resistant to quantum attacks. Grover's algorithm can speed up brute force attacks on symmetric keys, but it only provides a quadratic speedup, not the exponential speedup that Shor's algorithm provides for factoring. What this means for HKDF is that if you're using SHA-256, which classically provides 256-bit preimage resistance, in a post-quantum world it effectively provides 128-bit security due to Grover's algorithm. This is still considered secure for most applications. If you want more margin, you can switch to SHA-512, which would provide 256-bit post-quantum security. The HKDF algorithm itself doesn't need to change, just the underlying hash function might need to be upgraded to longer output lengths. However, the input key material to HKDF might be at risk in a post-quantum world. If your IKM comes from an ECDH key exchange, a quantum computer running Shor's algorithm could break that key exchange and recover the shared secret. This is why post-quantum key exchange algorithms are being developed and standardized. NIST has selected several post-quantum key exchange mechanisms including Crystal Kyber. Once these are deployed, you would use post-quantum key exchange to generate IKM, then use HKDF with SHA-512 or SHA-3512 to derive your working keys. Hybrid approaches are recommended during the transition period. You can combine classical ECDH with post-quantum key exchange, concatenate the two shared secrets, and feed that into HKDF extract. This provides security if either system remains secure. The TLS working group is actively working on hybrid key exchange mechanisms for TLS 1.3 that follow exactly this pattern. Your HKDF implementation doesn't need to change. You just need to feed it better input key material from quantum-resistant sources. For long-term data protection, consider that adversaries might be storing encrypted traffic now to decrypt later with quantum computers. This is called harvest now, decrypt later attacks. If your data needs to remain confidential for decades, start planning your migration to post-quantum cryptography now. Use HKDF with SHA-512 or SHA-3512. Ensure your input key material comes from quantum-resistant sources, and have a plan for re-encrypting data with post-quantum algorithms when they are fully standardized and deployed. Advanced use case hierarchical key trees. One powerful pattern enabled by HKDF is the construction of hierarchical key trees, where you have a root key at the top and derive layer after layer of child keys below it. This pattern is used in Bitcoin wallets, certificate authorities, and distributed systems. Understanding hierarchical key derivation helps you design scalable key management architectures. The basic idea is that from one root key, you can derive multiple child keys using different info parameters. Each child key can then become the PRK for deriving its own children, creating a tree structure. For example, you might have a root key that derives separate keys for development, staging, and production environments. Each environment key then derives keys for different services. Each service key derives keys for different users. This creates a three-level tree where compromising a leaf key doesn't compromise keys in other branches. Bitcoin's BIP32 standard for hierarchical deterministic wallets uses exactly this pattern, though with a slightly different KDF than HKDF. From a master seed, you derive a master private key. From that master key, you derive account keys using derivation paths like M/44/0/0. Each account key can derive billions of address keys. The benefit is that you can back up just the master seed, and from that single value, regenerate all your keys. This is much better than backing up thousands of individual keys. In cloud environments, you can use hierarchical key trees for multi-tenant systems. Derive a unique root key for each tenant from your master key using the tenant ID as the info parameter. Then each tenant's root key derives keys for their different resources. This provides strong isolation because tenant keys are cryptographically separated, yet you only need to protect one master key, and your KMS key rotation becomes easier too because you can rotate the master key and rederive all tenant keys rather than rotating thousands of individual keys. The mathematical property that makes hierarchical derivation secure is that HKDF is a one-way function. You can derive child keys from parent keys, but you cannot derive parent keys from child keys, and you cannot derive sibling keys from each other. This means that even if an attacker compromises a child key at the bottom of your tree, they gain no information about other branches of the tree. The tree provides both organizational structure and security isolation. When implementing hierarchical key trees, Be careful about your derivation paths. Use structured info parameters that encode the path from root to leaf. For example, tenant 123, service, API, purpose, encryption. This makes it clear how to derive any key from the root, and it prevents ambiguities. Also document your key tree structure so that operations teams understand the relationships and can respond appropriately if a key is compromised. Hierarchical key trees are powerful but require good operational practices to use effectively. Summary and best practices. We've covered a lot of ground on HKDF, from the fundamental mathematics to advanced use cases. Let's consolidate the key takeaways and best practices that you should remember when using HKDF in your systems. These guidelines distill the lessons from cryptographic research, real-world deployments, and security incidents into actionable advice. First, always use HKDF from a well-tested cryptographic library. Don't implement it yourself unless you are a cryptography expert and have a very good reason. Libraries like OpenSSL, Boring SSL, Libsodium, and the cryptography packages in Python, Go, Rust, and Node.js are all excellent choices. These libraries have been audited, optimized, and hardened against side-channel attacks. Using them correctly is much safer than rolling your own implementation. Second, use SHA-256 as your minimum hash function, with SHA-512 preferred for higher security or post-quantum resistance. Never use SHA-1 or MD5 for new systems. The hash function is the foundation of HKDF's security, so choosing a strong one is essential. If you need to match an existing protocol, use whatever hash function the protocol specifies, but for new designs, default to SHA-256 or SHA-512. Third, always use unique salts or unique info parameters to ensure different derivations produce different keys. The info parameter is your primary tool for domain separation. Include protocol names, version numbers, purpose identifiers, and contextual information like user IDs or session IDs. Structure your info parameters with linked prefixes or delimiters to avoid ambiguity. Never reuse the same IKM, salt, and info combination for different purposes. Fourth, protect the PRK as carefully as you protect the final derived keys. The PRK is a secret value that can derive all your working keys. Store it in protected memory, clear it when no longer needed, and never log or transmit it. If you need to store PRK long-term, encrypt it with a key from your key management system. Treat PRK with the same operational security practices you use for any cryptographic key. Fifth, don't use HKDF directly with passwords. If you need to derive keys from passwords, first use a password-based KDF like Argon2 or PBKDF2 with a high iteration count. Then use HKDF to expand that output. HKDF assumes high entropy input and doesn't provide protection against brute force attacks on weak passwords. Layering password-based KDFs with HKDF gives you both password strengthening and flexible key derivation. Finally, test thoroughly. Use the RFC 5869 test vectors to verify correctness. Use property-based testing to verify general properties hold. Test your integration with the larger system. Test for side channels and timing attacks. Have your cryptographic code reviewed by security experts. Make testing part of your CI/CD pipeline so every change is validated. Cryptographic bugs can be subtle and devastating, so invest in comprehensive testing. Thank you for your attendance. Please consider subscribing to the channel.